Hello there, and welcome to Earth's history, where the future unfolds as slowly and inevitably as the past, where continents drift like clouds across deep time, and where patience is measured, not in lifetimes, but in the slow breath of a restless planet. Tonight, we're traveling forward, not backward. We're journeying into a future so distant it seems like fiction, a time when the world map will look nothing like the one you know, when oceans will close and continents will collide, when the scattered fragments of Earth's crust will gather once more into a single landmass. This is the story of Pangea Ultima, the supercontinent to come, the next chapter in Earth's long cycle of assembly and dispersal. If you've ever looked at a map and noticed how South America and Africa seem to fit together like puzzle pieces, if you've ever wondered whether the continents were once connected, you've touched on a truth that goes deeper than you might imagine. The continents are moving. They've always been moving. They're moving right now, beneath your feet, slowly, imperceptibly, but inexorably. And that movement doesn't stop. It continues forward into the future, carrying the continents toward new configuration, new arrangements, new collisions that will reshape the face of the planet. Wherever you are right now, I hope you're settled, comfortable, ready to drift through time. Maybe you're lying in bed as the night deepens around you. Maybe you're sitting in a quiet room as the world outside settles into stillness. Maybe you're in that liminal space between thought and dream, where the boundaries of time dissolve and the mind can wander freely across millions of years. If this journey into deep time brings you peace, if it helps you see the world as a living, changing, patient thing, I'd be grateful if you'd like the video. Subscribe to the channel or share it with someone else who finds comfort in knowing that the story continues, that the Earth is still writing its narrative, that we are witnessing just one brief moment in an endless transformation. So settle in. Let your breathing slow like the movement of continent. Let your thoughts drift like landmass across an ancient ocean. And let's begin. Because 250 million years from now, give or take a few tens of millions of years, the continents will gather again. The Atlantic Ocean will close. The Americas will collide with Africa and Europe. Australia will crash into Asia. Antarctica will drift northward from its frozen isolation, and the world will be one land again, united, transformed, strange, and familiar all at once. Before we step into that distant future, before we watch the continents converge and collide, we need to understand where we are now, how we got here, and why the continents will inevitably come together again. Because the story of Pangea Ultima is not separate from the story of Earth's past. It's the continuation of a cycle that has repeated many times before, a rhythm as fundamental to our planet as the seasons or the tides. Though operating on timescales so vast, they dwarf human history, human civilization, even human evolution. Right now, today, the continents are scattered across the globe, separated by vast oceans. The Atlantic Ocean splits the Americas from Europe and Africa, growing wider every year as the seafloor spreads at the mid-Atlantic ridge. The Pacific Ocean, that immense body of water covering nearly half the planet, separates the Americas from Asia and Australia, though it's slowly shrinking as the Pacific seafloor subducts beneath the surrounding continent. The Indian Ocean lies between Africa, Asia, and Australia. The Arctic Ocean caps the North Pole. The Southern Ocean rings Antarctica. This configuration feels permanent to us. We're taught geography as if the continents are fixed, as if the map we memorize in school will remain the same forever. And on human timescales, that's essentially true. The continents move at rates of a few centimeters per year, roughly as fast as your fingernails grow. In a human lifetime, they might move a meter or two. In all of recorded human history, perhaps 50 meters, imperceptible, meaningless to our daily lives. But on geological timescale, that movement accumulates into something profound. A few centimeters per year becomes a few meters per century, a few hundred meters per millennium, kilometers in tens of thousands of years, hundreds of kilometers in millions of years, thousands of kilometers in tens of millions of years. Over 250 million years, continents moving at just a few centimeters per year can travel halfway around the globe, can close entire oceans, can collide with devastating force, can reshape the planet. This movement is driven by plate tectonic, the slow convection of the Earth's mantle beneath the crust. The mantle, that thick layer of semi-solid rock between the crust and the core, is hot, heated from below by the core and from within by radioactive decay. And like any fluid heated from below, it convects. Hot material rises toward the surface. Cool material sinks back toward the core. This creates circulation patterns, giant loops of flowing rock that operate on timescales of 10 to hundreds of millions of years. The crust, broken into plates, rides on top of this convecting mantle. Where hot mantle material rises and spreads, it pushes plates apart, creating mid-ocean ridges where new seafloor is born. Where cool mantle material sinks, it pulls plates down with it, creating subduction zones where old seafloor is consumed, recycled back into the mantle. Where plates slide past each other, they create transform faults, boundaries marked by earthquakes and offset terrain. And where plates collide, they create mountains, volcanoes, and eventually, supercontinent. This process, this plate tectonic cycle, has been operating for billions of years, since shortly after Earth's crust first solidified, and throughout that time, it has followed a pattern, a rhythm, a cycle that geologists call the supercontinent cycle. Continents gather together into a single landmass, a supercontinent. That supercontinent stands for a time, perhaps 100 to 200 million years. Then it breaks apart, its fragments drifting away from each other, opening new oceans. Those fragments drift for hundreds of millions of years, sometimes colliding with each other in smaller collisions, sometimes remaining separate. And then, eventually, they begin to converge again, drawn together by the same tectonic forces that pulled them apart, closing the oceans that opened, creating a new supercontinent. This cycle takes roughly 400 to 600 million years to complete, though the timing varies. Geologists have identified several past supercontinents, each representing a moment when the cycle reached its gathering phase. The most recent was Pangea, which existed roughly 300 to 200 million years ago, during the late Paleozoic and early Mesozoic eras. Before Pangea, there was Pannotia, assembled around 600 million years ago. Before that, Rodinia, around 1 billion years ago. And before that, other supercontinents whose names are less certain, whose configurations are harder to reconstruct, but whose existence is written in the rocks, in the patterns of ancient mountain belt, in the distribution of fossils and minerals. Each supercontinent was different, unique, shaped by the particular arrangement of the plates at that moment. But they all shared common features. They were vast, covering a significant fraction of the globe. They were surrounded by a single world-spanning ocean. They had extreme climates, with enormous deserts in their interiors, and intense seasonal variation. They shaped evolution, creating new environments, new challenges, new opportunities for life, and each eventually broke apart, scattered its pieces, and set the stage for the next cycle. We are currently in the dispersal phase of the cycle. Pangea broke up starting around 200 million years ago. First, a rift opened between Africa and South America, creating the southern Atlantic Ocean. Then, North America separated from Africa, creating the northern Atlantic. Laurasia, the northern portion of Pangea, broke into North America, Europe, and Asia. Gondwana, the southern portion, fragmented into South America, Africa, Antarctica, Australia, and India. The pieces have been drifting apart ever since, carried by seafloor spreading, by the opening of new ocean basins. But the dispersal phase doesn't last forever. Already, the continents are beginning to slow, to change direction, to move toward new collision. The Atlantic Ocean, which has been widening for 200 million years, will eventually reach its maximum extent and begin to close. The Pacific Ocean, which has been shrinking, will either close completely or be replaced by new ocean basins. The fragments that separated from Pangea will gather once more, drawn together by forces already in motion, by processes already underway, deep beneath the surface. And this is where we project into the future, where we use our understanding of plate tectonics, of the forces driving continental motion, of the patterns from past supercontinents, to imagine what comes next. Scientists have developed several models for the next supercontinent, each based on different assumptions about how the continents will move, which oceans will close, where the collisions will occur. The models have different names: Pangea, Ultima, Novopangea, Aurica, Amazia, each representing a different possible future configuration. Pangea Ultima, the model we'll focus on tonight, is perhaps the most dramatic. It envisions a world where the Atlantic Ocean closes, where the Americas swing back toward Europe and Africa, where the continents gather in roughly the same location where Pangea once stood. It's a return, a homecoming, the scattered family reuniting in the place they once left. The name itself suggests this: Pangea Ultima, the final Pangea, the last Pangea. Though of course it won't actually be the last, because the cycle will continue, because supercontinents assemble and break apart over and over, endlessly, as long as the Earth's interior remains hot and convection continues. But Pangea Ultima is perhaps 200 to 250 million years away, and the journey toward it begins now, with movements already underway, with continents already on collision courses, with oceans already beginning to close. So let's trace that journey, step by step, era by era, watching the continents drift and converge, imagining the world as it transforms, as the map you know dissolves, and a new map emerges. The first major collision in our future is already beginning. Africa is moving northward, driven by sea floor spreading in the South Atlantic and the gradual closure of the Mediterranean basin. The Mediterranean Sea, that beautiful blue expanse between Europe and Africa, is a remnant of a much larger ocean called Tethys that once separated the northern and southern halves of Pangea. Tethys has been closing for hundreds of millions of years as Africa drifted north, and the Mediterranean is what's left, the last gasp of that ancient ocean. In about 50 million years, perhaps less, the Mediterranean will close completely. Africa will collide with Europe, crumpling the land between them, pushing up enormous mountain ranges. The Alps, the Pyrenees, the Carpathians, all the mountain ranges that currently mark the boundary between Europe and Africa will be dwarfed by the new mountain created in this collision. These new mountains might rival or even exceed the Himalayas in height. Massive ranges stretching from Spain to Turkey, from Italy to the Black Sea, a wall of stone rising kilometers into the sky. This collision will close the Strait of Gibraltar, sealing off the Mediterranean from the Atlantic. Without inflow from the Atlantic, the Mediterranean basin will begin to dry up, evaporating under the hot sun, its water turning to salt, flats, and desert. This has happened before, during the Messinian salinity crisis about 6 million years ago, when tectonic movements temporarily closed the Strait of Gibraltar and the Mediterranean almost completely evaporated, leaving behind massive salt deposits. The collision of Africa and Europe will make that temporary closure permanent, transforming the Mediterranean from a sea into a vast lowland basin, perhaps dotted with hypersaline lakes, perhaps completely dry, a depression kilometers below sea level. As Africa continues to push northward, it will not only collide with Europe, but also rotate slightly, bringing its eastern coast closer to Asia. The Red Sea, that narrow body of water between Africa and the Arabian Peninsula, will close. Arabia, currently attached to Africa by only a thin strip of land, will weld fully to Asia, adding to the bulk of the Eurasian landmass. The collision will create more mountain, perhaps a northern extension of the East African Rift Highland, perhaps new volcanic chains as the African plate subducts beneath Asia. Meanwhile, in the Pacific, changes are already underway. The Pacific Plate, the largest tectonic plate on Earth, is subducting beneath the surrounding continents in a ring of subduction zones called the Ring of Fire. This subduction is consuming the Pacific seafloor, slowly but inexorably reducing the size of the Pacific Ocean. The ocean that currently covers nearly half the planet is shrinking, and over the next 100 to 200 million years, it will continue to shrink, perhaps eventually closing completely, perhaps being replaced by new ocean basins that open elsewhere. As the Pacific shrinks, the continents on its margins are drawn closer together. The Americas are moving westward, driven by seafloor spreading in the Atlantic. Asia is more or less stationary, or moving slowly in various directions, depending on the specific region. Australia is moving rapidly northward, driven by seafloor spreading in the Southern Ocean, and by the complex tectonics of the Indo-Australian plate. These movements will eventually bring the continents into collision. Australia will be the first to collide with Asia, probably within the next 50 to 100 million years. It's already close, separated from Asia by only a few thousand kilometers of ocean, a distance that seems vast on human scales, but is trivial on geological timescales. As Australia approaches, it will first collide with the islands of Indonesia, crumpling them, absorbing them, adding their mass to the growing landmass. Then, it will collide with mainland Southeast Asia, with Malaysia and Thailand and southern China, creating new mountain ranges, perhaps as dramatic as the Himalayas, which were created by a similar collision between India and Asia that is still ongoing. The collision of Australia with Asia will close the ocean basins between them: the Banda Sea, the Arafura Sea, parts of the Western Pacific, the islands of the Indonesian archipelago, currently scattered across thousands of kilometers of ocean, will be welded together, fused into a continuous landmass. Papua New Guinea will be joined to mainland Asia. The Philippines might be caught in the collision, accreted onto the edge of the continent. The entire region will be transformed, from an archipelago of islands to a solid block of land, from a maritime culture to a continental one. At roughly the same time, other collisions will be underway. North America and South America currently connected by the narrow Isthmus of Panama, will remain together, forming a single massive continent that geologists call the Americas, or sometimes the New World. This combined landmass will continue moving westward, closing the Atlantic behind it, and approaching Asia from the east. And Antarctica, currently isolated at the South Pole, covered by kilometers of ice, will begin to move. The forces driving Antarctica's movement are complex, involving changes in the surrounding ocean basin, shifts in mantle convection pattern, perhaps the opening of new rifts that push it away from its current position. But in most models of Pangea Ultima, Antarctica drifts northward, leaving its polar isolation, moving into warmer latitude. As Antarctica moves north, its ice will begin to melt. Not quickly, not all at once, but gradually, over millions of years. The continent beneath the ice will be revealed, a land of mountains and valleys, of lakes and rivers, of rock weathered by eons under the ice. Some models suggest that Antarctica will collide with Australia, the two continents joining after being separated for millions of years. Others suggest it will move independently, perhaps colliding with South America, perhaps with Africa, perhaps ending up somewhere unexpected, wedged between other landmasses in the new supercontinent. Now, let's move farther into the future, perhaps 150 million years from now. By this time, the Atlantic Ocean will have reached its maximum extent and begun to close. The Mid-Atlantic Ridge, that underwater mountain range where new seafloor has been forming for 200 million years, will slow its spreading, perhaps stop entirely. New subduction zones will form along the margins of the Atlantic, perhaps along the coasts of the Americas, perhaps along the coasts of Europe and Africa, perhaps both. Subduction is the beginning of closure. When a subduction zone forms, one plate begins to sink beneath another, consumed back into the mantle. As the subducting plate pulls the attached continent toward the subduction zone, the ocean basin begins to shrink. Slowly at first, then faster as the continents approach each other, drawn together by the pull of the sinking slab, by the inexorable force of the Earth's convection. As the Atlantic begins to close, the Americas will move eastward, back toward Europe and Africa. The distance between them will decrease, century by century, millennium by millennium. The Atlantic Ocean, which has been widening for so long, will begin to narrow. 50 kilometers per million years, 500 kilometers per 10 million years, 5,000 kilometers per 100 million years. The ocean that took 200 million years to open will close in perhaps half that time, compressed by the approaching continent. As the Americas approach Africa and Europe, the seafloor between them will be consumed in subduction zone. The oceanic crust, old and cold and heavy, will sink into the mantle, pulled down by its own weight. The continents, lighter and more buoyant, will ride over the subducting slab, approaching each other, eventually colliding. The collision will not happen all at once. Continents are large, complex, irregular in shape. They collide in stages, different parts meeting at different times. Perhaps South America will collide with Africa first, the two continents that once fit together like puzzle pieces reuniting. The collision will be slow by human standards, but catastrophic by geological one. The South Atlantic will close, the ocean floor consumed, the continents crashing together with the force of billions of tons, moving at centimeters per year. The collision will create mountains, enormous ranges rising where the continents meet. The rocks at the edge of each continent will be crumpled, folded, thrust upward, creating peaks kilometers high. The Andes, the mountains that currently run along the western edge of South America, will be joined by new ranges on the eastern side, created by the collision with Africa. The Atlas Mountains in North Africa, the Appalachians in North America, will be rejuvenated, pushed up again by the collision, growing taller as the continents compress. And beneath the mountains, deep in the crust, the rocks will be transformed by heat and pressure. Metamorphism will occur. Minerals recrystallizing, new rocks forming from old ones. Granite will form from the partial melting of crustal rock. Volcanoes will erupt along the collision zone, fed by magma generated by the subduction and compression. The collision will be marked by earthquakes, by tremors that shake the land, by the slow but inexorable reshaping of the surface. At roughly the same time, North America will collide with Europe. The northern Atlantic will close, the continents meeting somewhere in the middle of what is now the Atlantic Ocean, perhaps near where the Mid-Atlantic Ridge currently stands. The collision will fuse North America to Europe, creating a continuous landmass from what is now Alaska to what is is now Siberia, from what is now California to what is now North Africa. The collision will create new mountain ranges, perhaps rivaling the Rockies and the Alps, perhaps creating entirely new structures, unlike anything we've seen. The Great Plains of North America might be uplifted, transformed into highland. The lowlands of northern Europe might be crumpled into mountain. Coastlines will disappear as the ocean closes. Islands will be caught between the colliding continent, accreted, added to the growing landmass. And as these collisions occur, as Africa and the Americas reunite, the other continents will be drawn in. Asia, vast and ancient, will be pushed from the east by the closing Pacific. Australia, having already collided with Southeast Asia, will be part of the Asian landmass, adding its bulk to the supercontinent. Antarctica, drifting northward, will collide with one of the other continents, perhaps wedging itself between South America and Africa, perhaps colliding with Australia, perhaps ending up in an unexpected location. By 200 million years from now, perhaps 250 million years from now, the assembly will be nearly complete. The Atlantic will be closed, a memory preserved in the rock, in the patterns of mountain belt, in the fossils that show how creatures on opposite sides of what was once an ocean are related. The Pacific will be much smaller, perhaps closed entirely, replaced by new ocean basins that have opened elsewhere, perhaps on the opposite side of the supercontinent. And the continents will be gathered, fused, united into a single landmass. This landmass, Pangea Ultima, will be enormous, perhaps even larger than the original Pangea, because the continents have grown over time, accreted new material, built new crust through volcanic activity, and the accretion of island arc. It will stretch from pole to pole, or nearly so, covering perhaps a third of Earth's surface, possibly more, and it will be surrounded by a single vast ocean, a new Panthalassa, a world-spanning sea that covers the rest of the planet. The shape of Pangea Ultima is uncertain, dependent on the exact timing and sequence of collision, on movements we can't predict with certainty over such vast timescale. But in most models, it forms in roughly the same location where Pangea stood, centered near the equator, and extending into both hemispheres. Some models show it as a roughly circular landmass, others as a more elongated shape, others as an irregular assembly of merged continents with a complex, convoluted coastline. One possible configuration shows the Americas forming the western edge of the supercontinent, Europe and Africa forming the center, and Asia and Australia forming the eastern edge. Antarctica might be wedged in the south, or perhaps incorporated into the center, depending on its path. The Mediterranean basin, long since dried, might be buried beneath new mountains created by the collision of Africa and Europe. The Amazon basin, currently one of the world's great river systems, might be uplifted and transformed. The Great Rift Valley of East Africa, currently a place where the continent is beginning to split, might be welded shut by the assembly of the supercontinent. Another configuration shows a more complex assembly, with the continents arranged differently, perhaps with Asia forming the core, and the other continents arranged around it, perhaps with Antarctica in a more central location, perhaps with unexpected collisions creating unusual geometries. The exact configuration depends on assumptions about mantle convection, about the opening and closing of ocean basins, about movements that are difficult to predict over such long timescales. But regardless of the exact shape, Pangea Ultima will share certain characteristics with all supercontinents. It will have extreme climate, with vast deserts in its interior. It will have a limited coastline relative to its size, reducing the moderating influence of the ocean on its climate. It will affect ocean circulation, wind patterns, and the carbon cycle. It will shape the evolution of life in profound ways, and it will eventually break apart, scattering its fragments, opening new oceans, continuing the cycle. Let's imagine what it would be like to stand on Pangea Ultima, to walk across that future world, to experience its landscapes, its climate, its life. Picture yourself transported 250 million years into the future, standing on the coast of this new supercontinent, looking out at the vast ocean that surrounds it. The coast stretches in both directions, as far as you can see, a long, relatively straight line of shore, without the intricate bays and inlets and peninsulas that characterize modern coastline. This is because supercontinents have simple coastline, without the complexity created by the collision and dispersal of many smaller landmasses. The beach beneath your feet is made of sand, but the sand is different from what you're used to. The minerals have been cycled through weathering and erosion and deposition many times over the hundreds of millions of years since your time. The quartz is still there. Quartz is stable, persistent, but the other minerals have changed, transformed by the long processes of geological recycling. The ocean before you is warm, at least in the tropical and subtropical latitude. The water is blue-green, clear near the shore, but darkening as it deepens. There are no familiar landmarks, no recognizable shapes on the horizon. The ocean is vast, unbroken, stretching to the edges of the world. This is the new Panthalassa, the world ocean, and it covers more than 2/3 of the planet's surface. Behind you, the land rises gradually from the coast. Near the shore, the climate is moderated by the ocean, relatively humid, with seasonal rainfall. Vegetation covers the ground, plants that would look alien to you, but which serve the same ecological roles as plants in your time. Photosynthesizing, capturing sunlight, building biomass, supporting food webs. But as you walk inland, away from the moderating influence of the ocean, the climate begins to change. The rainfall decreases. The temperature swings become more extreme. Hot days and cool nights, scorching summers and cold winter. The vegetation becomes sparser, more adapted to drought, more widely spaced. And as you continue walking, days turning into weeks, weeks into months, you enter the interior of the supercontinent. This interior is a desert, but not just any desert. This is one of the largest deserts Earth has ever known, stretching for thousands of kilometers in every direction. An expanse of arid land so vast that it makes the Sahara look small. The ground is mostly bare rock and sand, with only occasional patches of hardy vegetation adapted to extreme aridity. The sky is often clear, cloudless, the sun beating down with relentless intensity. The temperature during the day can exceed 50 degrees Celsius in summer, hot enough to kill most unprotected organisms. At night, the temperature drops dramatically, sometimes below freezing even in regions near the equator, because there is no water in the atmosphere to trap heat, no clouds to insulate the ground. The temperature swing from day to night, from summer to winter, is extreme, more extreme than anywhere on Earth in your time. Rain is rare in the deep interior, perhaps falling only a few times per year, perhaps not at all for years at a time. When it does rain, it comes in brief, violent storms, the water running off the hard-baked ground, carving channels and gullies, flowing briefly before evaporating or soaking into the sand. There are no permanent rivers in the deep interior, no lakes, no standing water except perhaps in the deepest depression where groundwater seeps to the surface. Life here is sparse, but not absent. There are plants, though nothing like the lush vegetation of the coast. These are drought-adapted species, perhaps succulents storing water in thick stems or leaves, perhaps plants with deep taproots reaching down to groundwater far below the surface, perhaps annuals that spend most of their life as seed, germinating and growing and reproducing rapidly when rain falls, then dying and leaving seeds to wait for the next rain. There are animals too, adapted to the extreme condition. Perhaps reptiles, which are good at conserving water, which can tolerate high temperatures, which can remain inactive during the hottest parts of the day, and emerge at dawn and dusk when temperatures are more moderate. Perhaps mammals, if mammals still exist in recognizable forms, adapted with efficient kidneys, with behaviors that minimize water loss, with the ability to go days or weeks without drinking. Perhaps insects, arthropods, creatures that have always been good at surviving in marginal environments. And there are birds, assuming birds still exist, or whatever flying vertebrates have evolved in the intervening 250 million years. They have an advantage in the desert, able to fly long distances to find food and water, able to move quickly between the rare oases and resource patches. Their calls might be the most common sound in the desert, aside from the wind. The wind is constant in the interior, unbroken by mountains or forests for thousands of kilometers, sweeping across the flat expanses, carrying dust and sand, sculpting dunes, carving rocks into strange shapes. The sound of the wind is the voice of the interior, a low moan during calm periods, a howl during storms. Dust storms can arise suddenly, turning day into night, reducing visibility to zero, sandblasting anything in their path. But the interior is not uniform. There are variations, differences, features that break the monotony. There are mountain ranges created by the collisions that formed the supercontinent, rising like islands from the desert plain. These mountains capture what little moisture moves across the interior, forcing air to rise and cool, creating rainfall on the windward slopes, creating rain shadows on the leeward side. In the mountains, the climate is different, cooler at higher elevation, wetter on the slopes that face the prevailing wind. Vegetation is denser here, perhaps perhaps forests on the wettest slopes, grasslands on the drier ones, alpine tundra near the peaks. Rivers flow from the mountain, carrying meltwater from winter snows, carving canyons as they descend, creating oases where they emerge into the desert lowland. There are also rifts, places where the supercontinent is beginning to crack, where the forces that will eventually pull it apart are already at work. These rifts are valleys, long linear depression, where the crust is stretching, where volcanism is active, where geothermal heat rises from below. The climate in the rifts can be unusual, sometimes wetter than the surrounding desert, because the topography creates local weather patterns, sometimes hotter because of the volcanic activity. And there are ancient lake beds, remnants of wetter periods, when the climate was different, when rainfall was more abundant, when lakes filled the basins and rivers flowed across the interior. These dry lake beds, called playas, are flat expanses of cracked clay or salt, sometimes flooded briefly after rare rain, sometimes completely dry for decades or centuries. They're eerie places, silent and empty, the land stretching flat to the horizon in every direction. The only sounds the wind and the crunch of salt crystals under your feet. Walking across the interior of Pangea, Ultima would be an exercise in endurance, in patience, in appreciating subtle variations in an environment that seems monotonous. Days would blend together, the sun rising and setting, the landscape barely changing, but slowly, over weeks and months, you would cross different zones, different regions, each with its own character, its own microclimate, its own collection of adapted organisms, and eventually, if you walked far enough, you would reach the other side of the supercontinent, the far coast, where the land meets the ocean again, and the climate becomes more hospitable, more humid, more alive. The journey across the interior might take months on foot, covering thousands of kilometers of harsh terrain, testing your limit, showing you the extremes that Earth can reach when land is gathered into a single mass. But not all of Pangea Ultima is desert. The coasts, as we mentioned, are more hospitable, moderated by the ocean, receiving regular rainfall from ocean moisture carried inland by wind. In the tropical latitudes near the equator, the coasts might support lush forests, perhaps not unlike tropical rainforests in your time, dense with vegetation, rich with life, heavy with humidity. In the temperate latitudes, farther from the equator, the coast might support deciduous or coniferous forests, grasslands, wetlands, a variety of ecosystems, depending on local conditions, on rainfall patterns, on topography. These regions would be the most habitable, the richest in life, the places where complex ecosystems could develop and thrive. And in the polar regions, if Pangea Ultima extends that far, there might be ice, though perhaps not as extensive as Antarctica is today, because the climate of a supercontinent world is generally warmer than a world with dispersed continent, because the arrangement of land and ocean affects heat distribution, ocean circulation, and atmospheric patterns in complex ways. The climate of Pangea Ultima, like the climate of Pangea before it, will be influenced by its geography, by the size and shape of the landmass, by its position relative to the equator and poles. Supercontinents tend to have more extreme climates than dispersed continents for several reasons. First, the interior of a supercontinent is far from the ocean, far from the moderating influence of water. Oceans absorb heat in summer and release it in winter, buffering temperature swing. Land heats and cools more rapidly, leading to extreme temperatures. In the interior of a supercontinent, thousands of kilometers from any ocean, this effect is maximized. Summers are hotter, winters colder, and the daily temperature range is greater than in coastal regions. Second, the lack of interior seas means that moisture from the ocean doesn't penetrate inland. Rain falls on the coast, but by the time air masses move inland, they've lost most of their moisture. The interior becomes a rain shadow on a continental scale, a vast arid region starved of precipitation. Third, the size and position of the supercontinent affect atmospheric circulation pattern. The continents influence where air rises and sinks, where high and low pressure systems develop, where jet streams flow. A large landmass near the equator can disrupt the normal patterns of tropical circulation, creating monsoons, seasonal wind reversals that bring heavy rain in one season and drought in another. And fourth, the arrangement of land and ocean affects ocean circulation, the movement of currents that distribute heat around the planet. With continents dispersed, as they are in your time, Ocean currents can flow relatively freely, carrying warm water from the tropics toward the poles and cold water from the poles toward the equator, moderating global temperature. But with a supercontinent, ocean circulation is disrupted, blocked by the landmass, forced into different patterns that might be less efficient at distributing heat. The combination of these factors means that Pangea Ultima will likely have a climate more extreme than the climate of your time. The tropics might be hotter, the deserts larger and drier, the seasonal swings more pronounced. The coasts might experience intense monsoons, alternating between very wet and very dry seasons. The interior might be one of the most hostile environments Earth has ever produced, rivaling or exceeding the conditions of the original Pangea. But the climate will also depend on other factors that are harder to predict over 250 million years. What will the composition of the atmosphere be? How much carbon dioxide will there be? And how will that affect the greenhouse effect and global temperatures? What will the sun be like? The sun is gradually getting brighter as it ages, increasing its output by about 10% per billion years. In 250 million years, it will be about 2 to 3% brighter than it is now, adding to the heat the planet receives. What will life be like? Will there still be plants and animals recognizable as such? Or will evolution have taken them in directions we can't imagine? Life adapts, life changes, life evolves to fit the environments it encounters. The life on Pangea Ultima will be shaped by the climate, by the geography, by the long evolutionary journey from your time to that future. Speaking of life, let's consider what might exist on Pangea Ultima. This is perhaps the most speculative part of our journey, because evolution is not predictable, because chance plays a role, because we can't know what directions life will take over the next 250 million years. But we can make educated guesses based on trend, on patterns from the past, on the constraints imposed by physics and chemistry. First, let's consider extinction. The formation of a supercontinent is typically associated with massive periods when large percentages of species die out. This happens for several reasons. The reduction in coastline eliminates many shallow marine habitats, the environments where most marine species. The creation of extreme interior climate makes large areas uninhabitable for many organisms. The disruption of ocean circulation can lead to ocean anoxia, periods when parts of the ocean lose their oxygen and become dead zones. And the collision of continents brings previously isolated biotas into contact, allowing diseases and parasites to spread, creating new competition, disrupting established ecosystems. The formation of the original Pangea was associated with the Permian-Triassic extinction, the most severe extinction event in Earth's history, when perhaps 90% of marine species and 70% of terrestrial vertebrate species died out. The breakup of Pangea was associated with several smaller extinctions. The formation of Pangea Ultima will likely trigger another mass extinction, perhaps comparable in severity to past events, perhaps even more severe if other factors, like climate change or asteroid impacts, coincide with the continental assembly. But extinction is not the end of the story. Extinction clears ecological niches, creates opportunities, allows new groups to diversify and radiate. The survivors of the extinction will adapt to the new conditions, will evolve to fill the vacant niches, will become the ancestors of the dominant groups on Pangea Ultima. What will those groups be? Will there still be mammals, descendants of the mammals that dominate today? Will there still be birds, insects, reptiles, amphibians, fish, or will entirely new groups emerge, descendants of lineages that are currently minor, but which will find new opportunities in the post-extinction world? Let's consider some possibilities, some scenarios for life on Pangea Ultima, acknowledging that these are speculation, educated guesses, thought experiments rather than prediction. In the oceans surrounding Pangea Ultima, marine life will continue, adapted to the new ocean configuration, to the changes in circulation and chemistry. There will be plankton, microscopic organisms drifting in the sunlit surface water, photosynthesizing, forming the base of the marine food web. There will be fish, or whatever vertebrates have evolved to fill the niche of swimming predators. There will be larger predators, perhaps descendants of shark, perhaps entirely new forms. There will be filter feeders, organisms that strain plankton from the water, perhaps descendants of whales, perhaps new groups. The coral reefs, those biodiversity hotspots of modern oceans, might still exist, though the corals might be different, evolved to tolerate warmer waters, higher acidity, different chemical condition, or perhaps coral reefs will be replaced by entirely different ecosystems, dominated by different groups of organisms that build structures and create habitats for other species. On the coasts of Pangea Ultima, in the narrow belt of relatively habitable land near the ocean, life will be rich and diverse. The forests might be dominated by flowering plants, descendants of the angiosperms that currently dominate most terrestrial ecosystems, or perhaps conifers will make a comeback, adapting to the harsher condition, outcompeting the flowering plant. Or perhaps entirely new groups of plants will evolve, groups that are currently minor, but which will find success in the changed world. The animals in these coastal forests will include herbivores, creatures that feed on plants, and carnivores, creatures that feed on the herbivores. The specific forms these animals take will depend on what survives the extinction, on what lineages are available to adapt and diversify. If mammals survive and remain dominant, the coastal forest might be filled with descendants of modern mammals, evolved into new form, adapted to new ecological roles. But mammals have been dominant for only about 66 million years since the extinction of the non-avian dinosaurs at the end of the Cretaceous. In another 250 million years, who's to say they'll still be dominant? Perhaps another group will rise to replace them. Perhaps descendants of birds. Perhaps descendants of reptiles. Perhaps something unexpected. Consider birds. They are diverse, adaptable, found on every continent, in almost every habitat. They have already evolved to fill many ecological niches: predators, herbivores, scavengers, swimmers, runners, climbers. In a post-extinction world, with many niches opened up, birds might diversify further, might evolve into flightless ground-dwelling forms, might become the dominant large herbivores and carnivores, might replace mammals as the dominant terrestrial vertebrates, or consider reptiles. In the age of dinosaurs, reptiles dominated the land, the sea, and the air. That dominance ended 66 million years ago, but reptiles didn't disappear. They're still here, still diverse, still successful in many environments. In the hot, arid interior of Pangea Ultima, reptiles might have an advantage, their physiology well suited to water conservation, to tolerating high temperatures, to surviving in marginal environments. Perhaps reptiles will diversify, will become the dominant group in the interior, will evolve into forms we can barely imagine, or perhaps something entirely new will emerge. Evolution is full of surprises, of innovations that seem unlikely until they happen. Perhaps a group of insects will evolve to larger sizes, will diversify to fill niches currently occupied by vertebrates. Perhaps an aquatic lineage will return to land, will adapt to terrestrial life, will become a new dominant group. Perhaps fungi will evolve mobility, will become more animal-like, will create entirely new types of organisms. The point is not to predict exactly what will evolve, because that's impossible. The point is to recognize that evolution continues, that life adapts, that the biosphere of Pangea Ultima will be as rich and complex as the biosphere of your time, even if the specific organisms are different, even if nothing looks familiar. In the interior desert, life will be sparse, but specialized. The organisms that survive here will be extremophiles, creatures adapted to temperature extreme, to aridity, to intense UV radiation. They might resemble the desert organisms of your time in their adaptation, convergent evolution producing similar solutions to similar problems. Or they might be entirely different, new approaches to surviving in one of the harshest environments Earth has produced. There might be plants that have evolved underground photosynthesis, capturing light through translucent rock, or specialized structures, keeping most of their biomass buried to avoid desiccation. There might be animals that spend most of their time underground, emerging only briefly to feed or reproduce, living in burrows where the temperature is more stable and moisture can be conserved. There might be symbioses, relationships between organisms that allow them to survive where neither could survive alone. Perhaps plants with symbiotic bacteria that fix nitrogen or capture water from the air. Perhaps animals with symbiotic microbes that help digest the tough, fibrous plants of the desert. Perhaps entire ecosystems based on chemosynthesis rather than photosynthesis, drawing energy from geothermal sources in the volcanic rifts rather than from sunlight. The night sky on Pangea. Ultima will be different from the night sky of your time, though perhaps not dramatically so. 250 million years is a long time on human and geological scales, but it's a relatively short time in astronomical terms. The stars will have moved slightly, the constellations will be somewhat different, but the overall appearance of the sky will be recognizable. The moon, Earth's companion, will still be there, though it will be slightly farther away than it is in your time. The moon is gradually receding from Earth at a rate of about 3.8 centimeters per year, as tidal forces transfer angular momentum from Earth's rotation to the moon's orbit. In 250 million years, the moon will be about 9,500 kilometers farther from Earth than it is now. This might sound like a lot, but given that the moon is currently about 384,000 kilometers away, the change is only about 2.5%, a difference that would be imperceptible to the naked eye. But the moon's recession has other effects. As the moon moves farther away, its tidal forces on Earth weaken slightly, and Earth's rotation gradually slows. The length of a day is increasing by about 1.7 milliseconds per century due to tidal friction. In 250 million years, a day will be about 4.25 seconds longer than it is now, about 24 hours and 4 seconds. Again, this is a small change, imperceptible in daily life, but it represents a fundamental fact about Earth. The planet is slowing down, losing rotational energy to the moon, gradually winding down like a clock. The slower rotation will affect climate pattern, though the effects are complex and difficult to predict. The Coriolis effect, which influences the circulation of the atmosphere and ocean, depends on the rotation rate. A slower rotation means a weaker Coriolis effect, which could lead to broader circulation cells, different patterns of winds and currents, perhaps changes in the intensity and distribution of storm. But these are subtle effects, small perturbations on top of the much larger changes caused by the assembly of the supercontinent itself. The climate of Pangea Ultima will be dominated by its geography, by the arrangement of land and ocean, by the effects we've already discussed. The slower rotation will be a minor factor, a small adjustment to the overall pattern. The sun in the sky will look slightly brighter, slightly larger, though again the change will be small enough that you probably wouldn't notice. The sun is gradually increasing in luminosity as it ages, as hydrogen fusion in its core slowly changes its internal structure. 250 million years is not long enough for major changes. The sun is only about halfway through its main sequence lifetime and has billions of years to go before it exhausts its hydrogen and begins to evolve into a red giant. But the slow brightening is enough to add a small amount of heat to Earth's climate, perhaps enough to make the already extreme climate of Pangea Ultima slightly more extreme. Now let's consider what happens after Pangea Ultima formed, because the story doesn't end with the assembly of the supercontinent. Supercontinents are not stable, not permanent. The same forces that bring them together eventually pull them apart. The breakup of a supercontinent begins with rift, stresses in the crust, perhaps related to the insulating effect of the large landmass, perhaps related to changes in mantle convection, cause the continent to begin to stretch and crack. Rift valleys form long linear depressions where the crust is thinning, where volcanism is active, where earthquakes are common. At first, these rifts are dry, continental rifts like the East African rift today. But as the crust continues to stretch, as the rift deepens and widens, the floor of the rift drops below sea level. Water from the surrounding ocean begins to flood in, creating a new arm of the sea, a narrow body of water like the Red Sea or the Gulf of California. The process continues. The rift widens, the sea grows, and eventually a new ocean basin is born. Seafloor spreading begins at a mid-ocean ridge in the center of the new ocean. The fragments of the broken supercontinent drift apart, carried by the spreading seafloor, beginning a new dispersal phase of the supercontinent cycle. Pangea Ultima will last perhaps 100 to 200 million years before it begins to break up. The exact timing depends on complex factors, on how the mantle convection patterns evolve, on where the stresses in the crust accumulate, on chance events that we can't predict. But eventually, rifts will form, the supercontinent will split, and the fragments will drift apart, opening new ocean, moving toward new collision, beginning the cycle anew. Where will the breakup occur? That's impossible to predict with certainty, but we can make some guesses based on past patterns. Supercontinents often break up roughly where they assembled, following old suture zone, lines of weakness where continents previously collided. The breakup of Pangea followed some of the sutures from the assembly of Pangea, though not all of them. The Atlantic Ocean opened roughly where the Iapetus Ocean had closed, though not exactly. Perhaps Pangea Ultima will break up along the sutures from its assembly, the lines where the Americas collided with Europe and Africa, where Asia collided with the Americas, where Antarctica joined the landmass. Or perhaps the breakup will follow entirely new lines, new weaknesses in the crust, creating a configuration unlike anything we've seen before. One possibility is that the breakup will separate the supercontinent into northern and southern fragments, similar to how Pangea broke into Laurasia and Gondwana. Another possibility is that the breakup will fragment the supercontinent into many smaller pieces, creating a world with more continents than we have today, a more scattered configuration. A third possibility is that the breakup will be asymmetric, with one large fragment and several smaller ones, creating a lopsided world. Regardless of how it breaks up, the fragments of Pangea Ultima will drift for hundreds of millions of years, opening new oceans, closing others, sometimes colliding in smaller collisions, creating island chains and mountain ranges, reshaping the map again and again. And eventually, in another 400 to 600 million years, the fragments will begin to converge once more, drawn together by the relentless forces of plate tectonics, assembling into yet another supercontinent. That supercontinent, whatever it will be called, will be as different from Pangea Ultima as Pangea Ultima is from Pangea, as Pangea was from Rodinia. Each supercontinent is unique, shaped by the particular arrangement of plates, by the history that led to its assembly, by chance events and contingencies that we can't predict or control. But all supercontinents share common features, common patterns, common processes. They all have extreme climate. They all affect the evolution of life. They all eventually break apart. They're all part of the same cycle, the same rhythm that has been operating for billions of years and will continue for billions more, as long as Earth remains a dynamic, evolving planet. And that brings us to an important question. How long will this cycle continue? Will Earth always have plate tectonics, always have supercontinents assembling and breaking apart? Or will the process eventually stop? The answer depends on the heat in Earth's interior. Plate tectonics is driven by mantle convection, and mantle convection is driven by heat. The heat comes from two sources: primordial heat left over from Earth's formation, and radiogenic heat produced by the decay of radioactive elements like uranium, thorium, and potassium. Both sources are gradually declining. The primordial heat is slowly radiating away into space, never to be replenished. The radiogenic heat is declining as the radioactive elements decay, transforming into stable elements that don't produce heat. Earth is cooling, slowly but inexorably, and as it cools, the driving force for mantle convection weakens. Eventually, perhaps in 1 billion years, perhaps in 2 billion, perhaps longer, Earth will cool enough that mantle convection slows significantly, that plate tectonics becomes sluggish, or stops entirely. The crust will thicken, become more rigid, less mobile. The continents will stop moving, or move much more slowly. The supercontinent cycle will end, not because the continents have found a final configuration, but because the forces that move them have weakened, beyond the point where they can overcome the resistance of the rigid crust. At that point, Earth will become more like Mars or Venus, planets with thick, immobile crust, without plate tectonics, without the constant recycling of crust and the release of gases that plate tectonics provide. The implications for life are profound. Plate tectonics plays a crucial role in regulating Earth's climate, in recycling carbon between the atmosphere and the interior, in providing nutrients to the ocean, in creating diverse environments and ecological niches. Without plate tectonics, Earth's climate might become unstable, swinging between extreme greenhouse and icehouse conditions, or settling into a stable but lifeless state. The oceans might evaporate or freeze. The atmosphere might be stripped away or become too thick to support life. The planet might become uninhabitable long before the sun exhausts its hydrogen and enters its red giant phase. But that's a long time in the future, billions of years away. In the meantime, for the next billion years or so, Earth will remain a dynamic planet, with continents moving, oceans opening and closing, supercontinents assembling and breaking apart. Pangea Ultima is just one chapter in that ongoing story, one moment in the long cycle of assembly and dispersal. Let's take a moment to reflect on what this means, on the perspective that deep time gives us. When you look at a map of the world, when you see the familiar shapes of the continent, it's easy to think of them as permanent, as fixed features that have always been and always will be. But now you know better. You know that the map is a snapshot, a moment in time, that the continents are moving, that the configuration you see today is temporary, transient, destined to change. In 250 million years, the map will be completely different. South America and Africa, now separated by thousands of kilometers of ocean, will be joined. North America and Europe, now on opposite sides of the Atlantic, will be fused. Australia now isolated in the southern Pacific, will be part of Asia. Antarctica, now buried under ice at the South Pole, will be in a warmer latitude, perhaps covered with forests. And in another 250 million years after that, after Pangea Ultima has broken apart, the map will be different again. The continents will be scattered in new configurations, opening new oceans, approaching new collisions. The cycle will continue. The story will unfold. The planet will keep changing, evolving, transforming. This perspective, this understanding that nothing is permanent, that everything changes given enough time, can be both humbling and liberating. Humbling because it reminds us how brief our moment is, how small we are in the grand scheme of things. The entirety of human history, from the first stone tools to the present day, spans perhaps 2.5 million years. That's 1% of the time between now and Pangea Ultima. The recorded history of civilization, from the first writing to today, is only about 5,000 years, a mere blink in geological time. But it's also liberating because it reminds us that the world is larger than us, older than us, will continue long after us. Our anxieties, our conflicts, our daily concerns, all the things that seem so important and urgent are temporary, fleeting, insignificant on the timescale of continent. The continents don't care about our politics, our economies, our wars. They move at their own pace, following their own imperatives, indifferent to human affairs. There's a certain peace in that knowledge, a certain freedom. When you're stressed, when the world seems overwhelming, when you're caught up in the urgency of the moment, it can help to remember that continents are drifting beneath your feet at the speed your fingernails grow, that mountains are rising and eroding, that oceans are opening and closing, all on timescales that dwarf your worries and concern. And yet, paradoxically, this perspective also makes the present more precious, precisely because our moment is so brief, because the current configuration of the world is so temporary. It becomes something to appreciate, to cherish, to experience fully. This particular arrangement of continent, this specific collection of species, this unique moment in Earth's history will never come again. Once it's gone forever, replaced by something new, something different, something we can imagine but never experience. So take a moment right now to appreciate the world as it is. Look at a map and really see it, not as a fixed reference, but as a snapshot of a moment in deep time. Think about the fact that the Atlantic Ocean is widening, that Africa is colliding with Europe, that Australia is racing northward. Think about the fact that in 250 million years, all of this will be different, transformed, unrecognizable. And then go outside, if you can, and look at the land around you. Touch the ground, pick up a rock. That rock is part of a continent that is moving, imperceptibly, but inexorably, carrying you with it on a journey across the surface of the planet. In 250 million years, the place where you stand might be part of a mountain range, or submerged beneath an ocean, or locked in the arid interior of a supercontinent. The rock in your hand might be metamorphosed by heat and pressure, or eroded to sand and deposited on a distant shore, or subducted into the mantle and melted back into magma. Everything is moving. Everything is changing. Everything is part of a story that spans billions of years and will continue long after we're gone. And we are privileged to be here, now, in this moment, able to understand that story, able to project ourselves into the past and future, able to see the planet not as a static backdrop, but as a dynamic, evolving, living thing. This is the gift of geology, the gift of deep time. It changes how you see the world, how you understand your place in it, how you think about change and permanence, time and scale. It makes the familiar strange and the impossible inevitable. It humbles and inspires in equal measure. And as we come to the end of our journey into deep time, as we return from Pangea Ultima to the present, I hope you carry this perspective with you. I hope that when you look at a map, you see not just static shapes, but continents in motion. I hope that when you see a mountain, you think about the collisions that formed it and the erosion that will eventually level it. I hope that when you stand on a beach, you remember that this coastline is temporary, that the ocean is growing or shrinking, that everything is in flux. The story of Pangea Ultima is not just a story about the future. It's a story about the nature of Earth itself, about the fundamental processes that have shaped our planet for billions of years and will continue to shape it for billions more. It's a story about cycles and patterns, about assembly and dispersal, about the patient, inexorable movement of continents across the surface of a restless world. And it's a reminder that we are part of this story, participants in this grand narrative, witnesses to one brief moment in an endless transformation. The continents will continue their journey long after humanity is gone, but right now, in this moment, we are here to observe them, to study them, to understand them, to tell their story. And what a story it is. From Pangea to Pangea Ultima, from the scattered continents of today to the united landmass of the far future, from the opening of oceans to their closure, from the slow drift of plates to the violent collision of continents. It's a story of epic scale, of geological time, of planetary change. It's a story written in rocks and fossils, in mountain ranges and ocean basins, in the slow movement of the crust over the mantle. And it's a story that continues, that unfolds even now as you read these words, as the Atlantic widens by a few centimeters, as Africa pushes northward, as Australia approaches Asia. The story doesn't pause, doesn't wait for us to catch up. It proceeds at its own pace, patient and relentless, moving toward its next chapter, toward Pangea Ultima and beyond. So as you settle back into your daily life, as you return to the concern and routines of the present, carry this knowledge with you. Remember that beneath the surface, beneath the immediacy of now, there is deep time, vast change, patient transformation. Remember that the earth is not finished, that the story continues, that we are witnessing just one frame in a very long film. And maybe, on a clear night when you can see the stars, take a moment to think about the future, about Pangea Ultima, about the continents gathering once more, about the deserts and mountains and coasts of that distant world. Think about the life that will evolve there, the ecosystems that will flourish, the extinctions and radiation that will shape the biosphere. Think about the planet, continuing its journey through time, changing, evolving, transforming, long after we're gone. Because that's what Earth does. It moves, it changes, it evolves, and understanding that, truly understanding it, changes how you see everything. Thank you for joining me on this journey through deep time, from the present to Pangea Ultima, and back again. I hope you found it thought-provoking, perhaps even comforting in its own way. The knowledge that the Earth is patient, that change is inevitable, that cycles repeat, can be a source of peace in an uncertain world. If you enjoyed this exploration, if it helped you see the world differently, if it brought you a sense of perspective or calm, please consider liking the video, subscribing to the channel, or sharing it with someone else who might appreciate this journey into geological time. There are more stories to tell, more journeys to take, more perspectives on our dynamic, evolving planet. Until next time, may your dreams be as vast as geological time. May your perspective be as broad as a supercontinent, and may you find peace in the patient, inexorable movement of the world beneath your feet.